Welcome to this video. Today I will try and share with you what I learned regarding the rough Bergomi parameters. So we will be looking at the surface parameters and diagnostic matrices used to shape and understand market volatility. Let's begin with the observed reality, the volatility surface. Market option prices form a three-dimensional landscape rather than a flat plane. This surface exhibits a pronounced smile, cross strikes, and steep term structure over time. Our primary engineering goal today is to build the mathematical engine capable of dynamically replicating this exact structure. So, this leads us to the illusion of flatness and why the one-factor models fail. The classic Black-Scholes assumption models volatility as a constant. They consider it as a deterministic number represented visually by a flat plane. The fundamental one-factor law is that when only the underlying asset prices moves, the resulting implied volatility surface is rigid. A one-factor engine fundamentally cannot generate a volatility smile dynamically because it assumes a smooth, predictable world that contradicts the market reality. Historically, quants attempted to fix this with a deterministic patch known as local volatility or the Dupire solution. This approach models volatility as a deterministic function of time and strike. However, this leads to a dynamics failure. Local volatility accurately maps the surface for a single fixed time, acting as a frozen snapshot. As the market evolves, the real surface shifts and breathes, and local volatility cannot capture the complex dynamics of how the surface moves over time, which means we need a second engine. So, stochastic volatility. To capture the moving surface, we introduce a second independent factor where volatility itself becomes a random variable. Factor 1 represents the continuous random walk of the asset price, while factor 2 is the mean reverting random walk of the asset's variance. This dual engine architecture finally allows the volatility surface to dynamically change shape over time. These two engines do not operate in isolation. They form a tether that generates a macroscopic skew. The two factors are mechanically linked by correlation, and in the equity markets, this correlation is highly negative. The mechanism is straightforward. When the asset price drops, the volatility goes up. This interconnected physical system organically generates the macroscopic volatility skew observed in real options pricing. Yet, standard stochastic volatility introduces a resolution problem, failing the magnifying glass test, because traditional stochastic volatility creates a dynamic surface, but the math is intrinsically too smooth. So traditional stochastic so this creates the short-term bug where models like the Heston model fail to generate the extreme short-term skew observed in the market and cannot replicate the negative power law of the volatility term structure. The real market explodes in the short term, but these smooth models merely curve. So, to fix this, we apply the rough patch, which is the fractional Brownian motion. The volatility factor requires a fundamentally different engine by abandoning standard Brownian motion and introducing a Hertz parameter of h less than 0.5, the math increments becomes negatively correlated. The result is a jagged process that fluctuates violently over incredibly short time frames, perfectly matching the empirical roughness of realized historical volatility. This brings us to the evolutionary culmination of pricing options, the rough Bergomi or R Bergomi models. Um, Looking at our model pathology matrix, the black shows local volatility and standard stochastic volatility all fail to capture the full picture. The rough Bergomi model captures microscopic skew, surface dynamics, and short-term explosion, all with immense parameter efficiency. It covers the Markov property with forward variance while requiring minimal parameters, just 3 parameters plus the curve, to perfectly map the market. Now let's explore the toolkit, the rough Bergomi panels or parameters. The framework replaces complex arrays of interlocking math with a clean geometric control panel. With just one base curve and 3 scalar parameters, the H, the volatility of volatility, and the correlation, we gain total independent control over the topography of the volatility surface. So, starting with the first one, the forward variance, which serves as our canvas. Its function is to represent the initial forward variance curve. Topographically, it sets the baseline term structure and altitude of the entire surface. Its mechanism acts as the base expectation of future instantaneous variance, serving as a foundational blueprint before any stochastic sculpting begins. The second is the Hertz exponent, the grid, or the H. It represents the degree of roughness. It controls the decay and steepness of the short-term skew. So mechanically, a lower parameter, less than 0.5, violently sharpens the short-dated smile, solving the magnifying glass failure of standard stochastic volatility models by determining how fast the skew flattens over time. For the volatility of volatility or the flex, its function is the volatility of volatility. So this controls the overall curvature, the curtices, and the convexity of the smile across all maturities. Mechanically, it dictates the magnitude of variance fluctuation, so higher values bend the wings of the volatility surface higher, effectively increasing the premium for extreme out-of-the-money options. And for the tilt or the correlation, this like a function as the correlation between the asset price and volatility. It shifts the asymmetry and relocates minimum point of the volatility smile. Mechanically, a highly negative value heavily tilts the surface, making downside put options structurally more expensive than the upside calls. So, by symmetrically combining these tools, we achieve the parameter morph. By sequentially layering these parameters over the base canvas, the rough Bergomi allows quantitative engineers to morph a flat plane into an exact replica of empirical market conditions layering on the grid, the flex, and the tilt. But, however, even with these tools, we operate in a latent world or decaying world and are essentially flying blind. We have the best tools, but there is still a fundamental problem. The volatility is decayed. So unlike stock prices, the instantaneous variance is mathematically invisible and cannot be directly observed or touched. We are operating a machine where the core material we are shaping is entirely hidden from our view. To navigate this, we rely on the shadow diagram, because this one here, because volatility is hidden, we can only measure the shadow it casts into the observable world. So, for example, traded derivative prices like options, variance swap, and like VIX futures are the visible projections of the hidden volatility dynamics. To know the shape of the latent object, we must study the contours of its observable shadow. This leads us to the ultimate challenge: calibration, or the inverse problem. Calibration is the computational process of reverse engineering the latent world. We systematically tweak our rough Bergomi control dials to generate simulated model shadows, which we compare to the actual traded market shadow, and then apply algorithmic error correction. The loop terminates only when our model's mathematical shadow perfectly cover the actual ground truth of the market surface. So when done correctly, historical testing confirms the power of the rough Bergomi framework with incredibly sparse parameterization, because we use just 3 scalars and the forward curve. The model consistently hits the moving target at the, for example, the SPX volatility surface across the maturities. It captures the negative power law, maintains the Markov property via forward variance, and aligns theoretical arbitrage-free pricing with empirical reality. Ultimately, this gives us the ultimate topography. So the evolution from Black-Scholes to rough Bergomi is the transition from assuming a flat world to mastering the rugged reality. By acknowledging the extreme roughness of variance and utilizing a dual engine architecture, financial engineers finally possesses the precise tools to accurately map and price the true topography of risk.